Hello students, in this video we'll see several examples of properties of complex logarithms which either work for the general multivalued logarithm or fail for the principal logarithm. So let's recall the function log, which maps the complex plane minus the half line, 0 to infinity, into c by log z, is the ordinary logarithm of the modulus of z. That's a real valued thing, so the log of a real number makes sense. The log of a non-negative real number, like modulus of z, makes sense, plus I argument of z. And now we recall, of course, that this argument of z is multivalued, right? This is multivalued. And then, okay, that's beautiful, right? And I know that this is an inverse of the exponential function, but the inverse of the exponential is multivalued because the exponential is periodic, right? Excellent. Okay, so this, in other words, we have the property that e to the log of z is equal to z, but remember the e is periodic now, 2 pi periodic, okay? 2 pi periodic, excellent. And then we have the principal branch, this is the multivalued logarithm, and we have the principal branch, principal log. The principal branch is what? Principal branch is just log log of z, is going to be just the ordinary log of the modulus of z, right? So it's a little bit, I'm extending the log to the complex plane via this argument here plus I, and the principal argument of z. So here argument of z is between negative pi and pi, and of course we know, of course, that this principal can include pi over here, but we're going to not allow that value since it's going to be on the negative half line, right? So the principal argument gives me those values, but we're never going to actually have that value of pi, right? Because the logarithm is going to jump at that point, and we're going to see how that jump is going to induce, it's going to lead to the failure of several properties, okay? So now, note, here's a proposition, log, log of z1, z2, is the log of z1 plus the log of z2. Now this is okay because these are multi-valued things. So how does the proof of this fact go? The proof of this goes as follows. So the log of z1, z2, okay, is going to be the what? Is going to be the ordinary log of the modulus of z1, z2, plus I, the argument, the multivalued argument of z1, z2, okay? What is this equal to? This is equal to the log of, this is the regular logarithm of modulus z1 plus the log of modulus z2. And then I arg, so arg is multiplicative, okay? So I arg z1 plus I arg z2, okay? So now these two terms over here, these two terms over here, I overshot my arrow. And this term, give me the what? That's the log capital of z1 plus the log capital of z2 from these guys over here. Excellent. And that proves our result. Okay. However, there's an anti-result to this. What's the antithetical result? Remark. The principal log of z1, z2 is not equal to, in general, the log of z1 plus the log principal of z2, okay? And now how do you see that? Well, I'm going to choose z1 to be e to the I pi over, let's do pi over 3 pi over 4. And let's choose z2 to be the same thing, e to the I 3 pi over 4, okay? They're the same values. So if I multiply these two numbers, what will happen? Well, the log of z1 is just going to be what? The log of z1, that's 3 pi over 4 is between negative pi and pi. So over here, on the right-hand side becomes what? The right-hand side is going to be 3 pi over 4, 3 pi over 4 plus 3 pi over 4, which is 6 pi over 4. 6 pi over 4 is 3 pi over 2. So that's 3 pi over 2. But z1 times z2 is just going to be e to the I what? This is going to be the log of e to the I 3 pi over 2. But 3 pi over 2 is not a principal argument over here. That falls outside of that range over there. So this is going to give me the what? It's going to be the negative pi over 2. So negative pi over 2. So one side of this equation is negative pi over 2. The other side of the equation is 3 pi over 2. So the log of z1 times z2 is not in general equal to the log principal of z1 plus log principal of z2. So that shows that there's a failure. So the property works for the multivalued logarithm, but it fails for the principal logarithm. Okay, excellent. And then of course you get the same sort of thing with powers, right? So example over here is, let's compute the log of I cubed. Well, I cubed, that's the same thing as just the log of negative I, right? And the log of negative I, by the same exact reasoning over here, that's down over here, so that's just going to be what? That's going to be negative. It's going to be I and then pi over 2 with a negative sign. So negative I pi over 2. Excellent, okay? That's the argument of negative I. But what is 3 times the log of I? 3 times the log of I, for example, is going to be 3. The log of I is going to be I times pi over 2. Principal log. So that's going to be 3 pi I over 2. And clearly those things are not equal to each other. So it's not the case that the log of z to the n is not equal to, in general, the log n log z to the n. So those ordinary rules for logarithms fail for the principal branch, right? So those rules fail for principal branch. And now what this also allows me to do is this allows me to actually define power functions, right? So how do we define power functions using this logarithm? So what are power functions? Power functions would be z to the power c, where c is not necessarily an integer, right? So c over here is just going to be any complex number. How would I define something like this? By definition, what this is the following. By definition, this is going to be, as we would for ordinary power functions, going to be e to the c principal log of z. So in other words, this is only defined, so c to the z, so f of z, which is c to the z, is defined on c minus the half line, negative infinity to 0, like that, okay? Now that's a cool definition because we get some sort of a nice sort of like math parlor tricks, right? Where, for example, you could say, well, what would I to the I be, for example? Well, I to the I would be e to the I log I. But of course, the log of I we know is what? The log of I was I pi over 2. So this is e to the I and then I pi over 2. But I times I is negative 1. So this is e to the negative pi over 2. We get this fun fact that I to the I is e to the negative pi over 2. So it maybe seems sort of strange, but the way the logarithm works, right? The logarithm and the exponential, it's all about the argument, right? So I can construct all sorts of examples where the argument is being shifted by the appropriate amount. And when the argument is shifted by the appropriate amount, what's happening is you can sort of see the structure. Notice, of course, that these things over here differ by what? Differ by 2 pi, right? So in other words, you can show in general that these things will agree up to this factor of 2 pi n, or an integer multiple of 2 pi, right? But of course, what we're really dealing with here is the natural sort of domain for a logarithm is really actually a Riemann surface or a Riemann sheet, right? So there's a sheet where the logarithm is, the multivalued function is defined in a more natural setting, where multivalued outputs are permissible, right? So in other words, the key takeaway from this should be the following, should be that once you define the principal branch of the logarithm, it's a continuous function, right? So in other words, there's not allowed to be jumps in the argument. So if there's not allowed to be jumps in the argument, the product rule and the power rule for logarithms will fail in general for the principal branch of the logarithm. Thank you very much.